Here's the tangent plane at this point, right? At this particular point, which I'm going to mark with this star, x is this value of x, y is this value of y, and z is this height. Are we good? We could even do this. Ding, ding, ding. This is the point P naught. All good? Looking at you too, because we were doing a bunch of geometry at the end of last time. Okay, so we have this. So the first thing I want to do is I want to figure out how I can come up, well, the thing I want to do is figure out how I can come up with the slope of this tangent plane at this point, which is sort of marked here, like this. How do I do that? I'm going to take two slices. I'm going to take a slice along the x-axis. If I want to take a slice along the x-axis, or I should say, I want to take a, let me figure out which variables to do first. I want to take a slice along this plane. What plane is this? YZ. So I want to pick a value of x and take a YZ slice. I also want to take a slice along this plane, which is the XZ. So I'm going to look at x and z first. Here I go. Goodbye, football. No one in this classroom is from DEET, the football frat. This would be. Oh yeah. Oh, I'm sorry. American football. Because I was thinking about how the rest of the class. Soccer football. Okay, so I'm doing a mild job of stabbing myself here. Right, but I really do this to show a point, which is that if you take such a slice, okay, and now I'll have to bring paper towels. I'm going to take that slice, and it's going to be here. Bear with me because it's all right. You might want to come to this side now. Okay, so here's the slice on which plane?
The
XZ, right? That curve looks like more or less, right? And at our point of tangency, sorry, at our point where we want to find the tangent plane, that's here. Okay, so what are the coordinates of this point? What's x? So if P naught is x naught, y naught, z naught.
X naught.
Yeah. So this is x naught,
y naught, z naught,
y naught, z naught.
Oh, okay.
This is the xz plane, though. Remember.
So it's only x naught and z naught.
Right. So we're going to move. If our tangent line here goes this way, how would you write that line's direction as a vector? What are we varying? X and z, right? Okay.
Yeah, use a parametric.
You could use a parametric. I'm going to be a little bit more cunning here, potentially. I'm going to take a step of 1 in the x direction. Okay. Does this vector have a y component if it's on the xz plane?
No.
No.
So 0.
0. Okay. And if I take a step of 1 in the x direction, by how much does z change?
None.
There's a quantity that tells us the rate of change of z with respect to a change in x.
By derivative of x.
Yeah, dz by dx,
Yeah. Yeah.
right? Or df by dx. I use z and f interchangeably. So this is dz by dx. Is everybody cool with this being the vector? Maybe the positive x should go this way, sue me, but more or less we got it. Okay, cool. Now, bearing in mind that, I'm going to lift this.
Wait, so we just say that dx over
dz by dx?
No, the first one, the 1.
Yeah.
Like, how do we get that one?
So what I'm saying is this vector points in the direction. So what's the slope of the tangent line?
The slope
Of this tangent line? If it's a function with z and x in it.
Confused.
How do you take the slope of a tangent line? Think single variable calc, because this is a single variable function.
It would just be
D.
It would be the derivative, right?
dy naught over.
So the derivative is the rate of change of z with respect to x, right?
Yeah.
That means that if I take one step in the x direction,
Okay.
z changes by dz.
Wait.
What's the slope of this? If the z component is dz by dx and the x component is 1?
GC.
It was dz by dx divided by 1, which is dz by dx.
Oh, okay.
Does that make sense? Like if you want to make a vector in the direction of the derivative, you go one step in x and the derivative in y. Alright, so we're at this slice.
So we have the derivative in z.
What was that?
So
We put, yeah.
Sorry.
For example, if I wanted a vector that points in the direction of the line with slope 2, what would its x component be? And then its y component? Yeah. So a line with slope 5,000. 5,000, yeah. A line with slope dz by dx, 1 comma dz by dx. However, it's 3D, so I need to give the y component 0 because I've taken the slice. All good? Okay. What do we need to do next, other than mess up Robin's seating area? What slice are we going to take now? And the cake is a lot more forgiving now because it's been out for a while. And if I do this, I actually meant for them to fit into each other, but that's going to be tricky. But you can imagine me doing this. But I'm not going to because I think I'm going to break it. All right, so here we go. Okay. Green marker and coming over to this side. Excuse me. So same idea. Here's our curve at the point. Here's the curve. Here's the point of tangency, E naught. Coordinates x naught, y naught, z naught. What plane is this now? How are we slicing? YZ. So give me the vector that is tangent to this curve. What's the x component? So it's a slice.
0.
0. Okay, and then 1, and then
dz by
dy. Okay, so I have two vectors. Two chocolatey vectors that don't line up as well as I would want them to, but imagine that these are overlapping. Actually, aha. Okay, do you see we have these two vectors? Yes, and both of these vectors are tangent to the plane, just along different directions. Do people agree?
Can I make a plane with those two vectors?
Brilliant. If I have these two vectors that are tangent, what can I do? I can make a plane with those two vectors. If I make a plane with those two vectors, what am I going to get?
a plane tangent to the point.
A plane tangent to the point. And how would I do that mathematically with these two vectors that we found? You cross them, you're going to get, which is better here. And that's a normal vector, and you have the equation of the plane. Okay. Does that conceptually make sense for finding the equation of the tangent plane?
Yes.
Okay. Very cool. All right, everybody, grab some bowls from the kitchen and let's serve up. And